The next topic in section 1.7 is piecewise functions. Now these are going to be functions where instead of there being one formula that we apply for every input, we have multiple formulas, sometimes just two, sometimes more than two, and which formula we use depends on what the input is. So as an example, let's just suppose that f of x is x squared plus 3 if x is less than or equal to 2. But it's x minus 5 if x is bigger than 2. So these are the two different formulas that we can use, and then these inequalities tell me which rule, when to use which rule. Let's just practice evaluating this function. Let's say I wanted to evaluate f at 0. So I wanted to find the y-intercept. Well, what I'd have to do first of all is I'd have to say, where does 0 fall? 0 is less than or equal to 2. So that tells me I'm going to use the top rule. Okay. So I use the top rule because the input that I'm plugging in is less than or equal to 2. And so, of course, I'll replace that x with an input box, and I'm plugging in 0. So 0 squared is just 0, and I would get 3. Let's say I wanted to evaluate f at negative 6. Again, I'd look at where does negative 6 fall? Negative 6 is also less than or equal to 2, and so I'd use, again, the top rule. And so I'd get negative 6 quantity squared is 36 plus 3. That would give me 39. Now let's say I wanted to evaluate f at 5. Well, now 5 is bigger than 2, and so I'd be using the bottom rule. And so now I'm just plugging in 5 for x, and so I would get 0. Okay. So which rule I use depends on what value I'm plugging in. Let's say I wanted to evaluate f of 2. 2 is kind of an interesting x value because that's where we change rules. But you'll notice this inequality was inclusive. That says we're using the top rule when x is 2. This was a strict inequality, so 2 is not bigger than 2. So I would be using, once again, the top rule. And so we would get 2 squared plus 3. That's going to be 4 plus 3. And so that's going to be 7. Okay. So that's how we can work with a piecewise function. What I'd like to do is see if we can graph this function. Now I ultimately want to graph f of x, but I'm going to do this in 3 steps. I'm first of all just going to graph x squared plus 3. Now, I know what that looks like. That's just my basic squaring function, except we've moved it up 3 units. So instead of the vertex being here at the origin, the vertex would be here at 0, 3. And so I'm going to have my basic parabola, like so. Now, part of my graph is going to look like that. And the part of the graph that's going to look like that is where x is less than or equal to 2. So 2 is a rather important x value here. If I were to plug in 2, we saw a moment ago that we would get 7. So the point 3, 4, 5, 6, 7. So we're at this point here, 2, 7. Now I want to have this function, so I want to have that graph, if x is less than or equal to 2. So that's going to include that point and all of the bits to the left of that point. So I'll essentially have the left part of that graph up until and including that point. Now let's sketch the bottom rule. If I sketch y equals x minus 5. Now that's just a line. The y-intercept is going to be negative 5. And the slope is 1. So I would come up 1 over 1 and then connect the dots. So there's that line. Now I want to have that line if x is bigger than 2. So let's see where we are at 2. At 2, we would be at 2, negative 3. But this time, I don't want to include that point. So I'm going to put an open circle there. That's my cutoff point, but it's not going to be on the graph of my function. So that's where we'll start, and then I want the part of this function that goes to the right of that, giving me x values that are bigger than 2. So now I'm ready to put the pieces together and sketch f of x. So I can see at 2, I'm actually going to have a point up here at 7. 1, 2, 3, 4, 5, 6, 7. So there's my point 2, 7. And to the left of that, we're just on this parabola, like so. So I'd want to plot the vertex because that's an important point. So I'd want to make sure that was at 0, 3. And I definitely want to plot this point 2, 7, which is where this parabola stops. And then we pick up, we don't have a point at 2, negative 3, but we're going to have a hole there. And then from that point on, we're just getting a line. So we have this funny looking graph. Kind of makes sense that we call it piecewise because it comes in 2 pieces. Here's the parabola piece, and here's the linear piece. Okay. You'll notice that when we change from this rule to this rule, the graph actually jumps. And it's very important when you do have a jump like that, that you make it clear whether there's a point or not a point. If there's not a point, there will be a hole there. So this says there is no point there, but it's necessary to draw that. The reason is, if I tried to just say that I was getting arbitrarily close to this point, but there was no point there, it's hard to tell exactly where I stopped. When I put an open circle here, that's saying, oh, I stopped at exactly 2, negative 3. There's no point there, but then arbitrarily close to that, we pick up with the line. And here, since there's a filled in point, we got exactly to the point 2, 7. Now, there's no need to put an open circle here to indicate that there's not a point there, because there's no reason for me to expect there to be a point there. But if I follow this line in, I would be expecting there to be a point here at 2, negative 3. It's necessary to have an open circle there to say that's the point where we're starting our line, but that starting point isn't included. So it's the line from that point on, not including that point. All right, this particular function jumps when we change rules. We've actually already seen an example of a piecewise function that doesn't jump when we change rules. We said that if we have f of x equaling the absolute value of x, it's possible to write that as a piecewise function, because the absolute value just gives us x if x is bigger than or equal to 0. But it gives us the opposite of x if x is less than 0. Now, if I were to graph this using this technique of just graphing each rule and then putting the pieces together, y equals x looks like this. That's just a line of slope 1 through the origin. And if I want the part of that graph where x is bigger than or equal to 0, I'm going to have a point here at the origin, and then just the right half of that line. Now, if I sketch y equals the opposite of x, that also gives me a line, but that gives me a line of slope negative 1 through the origin. And if I want just the part where x is negative, I would not have a point at the origin. There would be a hole there, and then I'd have just the left part of this line. Now, when I go to put those pieces together, I'm actually going to graph this part first. Here's the left half of my graph. But when I graph the right half of the graph, I fill in that point. So on the left half, on this part, there's no point there. But when I graph the right half of the graph, I put a point at exactly the same location, as this part had a hole. So it fills in that point, and so there are no holes in the graph. That's a hole that got filled in, and we would say this is what we call a continuous function. It doesn't jump to get from one piece to the other because the two pieces connect. Okay, so that's piecewise function. What I want you to do next is try these out with the questions that I've got on the worksheet. So if you've got the worksheet already and you've got those questions written down, you can actually just stop this video and go right there. Do questions 1 and 2 under piecewise functions before you tune into the next video. If you don't have the worksheet printed out, I'll put those problems up on the board for you right here. So f of x is x squared minus 3 if x is less than 1, but it's the cube root of x if x is greater than or equal to 1. And I'm asking you in part A, evaluate f of negative 3, B, evaluate f of 1, C, f of 8, and D, to graph f of x. All right, in question 2, we're letting g of x, this is going to be one that has 3 parts to it. So we're going to have x cubed if x is less than or equal to negative 1, 2x plus 3 if x is between negative 1 and 1, and 1 over x, the reciprocal function, if x is bigger than 1. So one piecewise function with 2 pieces, and then one piecewise function with 3 pieces. For part 2, I'm just asking you to graph g of x. All right, so try those problems and then tune back in and we'll work through them together.